Okay, so welcome everybody to our Thursday seminar. Today, we are very happy to have with us Matteo Baggioli from the house. So he needs no introduction, although I feel I should introduce him as one of the founders and promoters of the famous HoloTube, together with Daniel Arean, who is also here. Which is, I think, is right now we are on Zoom and we are used to it, but I think this is a beautiful example of how to adapt quickly to a situation like the pandemic, because this HoloTube started as a quick reaction to the fact that we had to cut a workshop in two, cut it, just stop it in the middle of it because of the Spanish confinement in March. And Matteo and Daniel decided to finish the workshop online, and this grew into this very nice series of seminars, and even with a sort of workshop vocation from time to time about applied holography. And I think it's a great story, and I would like to congratulate you for that. So welcome to this much more humble environment or scenario of the IFT webinars, but it's yours. So go ahead, please.
Okay, so thank you very much for the introduction and for mentioning the HoloTube. So I'm very happy to spread some of the work I'm doing with you guys, even though I'm from the house. Probably, we are so many that it's not easy to keep track of everybody. So I think it's nice, something like that. So yeah, I want to start with some disclaimer. So my expertise is basically applied holography, but today I will not talk about applied holography. Maybe fortunately, maybe unfortunately, you can decide. And I will also not talk about several things which are, discussed a lot in theoretical physics, in IFT and wherever. So I will not discuss things that we cannot see by eyes and which are very far from us. And I will not discuss things which are not proven to exist and cannot be measured. But on the contrary, I will have a much more humble, let's say, task, which is I will talk about something that you could see with your eyes having a walk at the beach. So, and I will try to convince you that even if you constrain yourself to consider the kind of objects, macroscopic objects that you see around you during your walk at the beach, there are plenty of open questions which are maybe not so famous and maybe not so fashionable, but they are indeed quite interesting. And the way I will do that is basically paraphrased in a very nice way by a quote by Albert Einstein that I like a lot, even though I didn't tattoo it yet. So everything should be made as simple as possible, but not simpler. And I will try to apply this Einstein quote to several systems that we see in nature, which appear very differently from the macroscopic point of view. And I will try with you to discuss and, let's say, explore all the methods, and in particular effective methods, to describe them. And yeah, so the system that I have in mind, I made here kind of a list. Some of them are very known, some maybe a little less, and I will get into the details later. So I will talk about liquids, I will talk about solid, I will talk about glasses, and I will talk about quasicrystals. And I think the only one that needs an introduction is quasicrystals, and we will get to there. Now let's try to understand why this quote by Einstein described very well the idea of effective field theory. Well, the quote is made of, let's say, two steps. So the first step is that everything should be made as simple as possible. And this is indeed the idea of effective theory. So imagine you have your problem and it's well represented by this kind of black box, whatever problem it is. If you are a cosmology, it can be some universe problem. If you are a string theory, your UV completion of gravity. If you are a particle physicist, can be the beyond standard model corrections to the standard model, etc. So the important thing is that whenever you consider this black box, of course there are terms that you consider and on which you build your theory, and terms that usually you avoid. So this is done usually at the level of the action, if the action is available, or you know, at the level of the equations. And the terms that usually you forget, the famous dots that we put in all the equations, well, we forget it for several reasons. And the main reason is that in a way or in another, these terms are suppressed. And they can be suppressed basically because of various reasons. But at the end of the day, everything boils down to the fact that they are more energetic in a sense. And what we are left of, at least at the, you know, at the first step, is to understand this black box from the low energy point of view. And the terms that we keep are the terms that are most relevant, and they are most relevant not only in the stricto sense of the word, but even in the RG flow sense of the word. And everything which is suppressed because it's either faster, it's smaller, it's heavier, etc., etc. So this is the first, basically, step of this Einstein quote. But then there is a second step, which is very important, which is everything should be made as simple as possible, but not simpler. So this means that these terms that I denoted here as A, B, etc., are not, let's say, random. We cannot decide which terms to include there and which terms to not include. And the big question is somehow what can or what we actually should write there. So there are two kind of rules, which are the fundamental rules of effective theories. And so the first one is that you have to impose some symmetry to start with. So you have to choose which kind of system you want to consider. And you have to tell me exactly which are the symmetries of the system. Once you have done that, it's clear that the terms that you can include must be all the terms respecting the symmetries. And here, just for you, I made very simple examples. Imagine you want to have some kind of shift symmetry. Imagine, for example, you want a scalar field theory where the scalar is invariant under a shift, let's say constant shift. It's clear that you cannot put a master, right? So the symmetries tells you which kind of terms you have to put here, but it's even more, the symmetry tells you all the terms that you have to put there. So you are not allowed, unless you have a very strong reason or a strong argument, to not put there some of the terms allowed by symmetry. So this looks like, you know, a kind of big zoo, and it looks like it's not that powerful, right? But as I will show you, it's very powerful, and of course, most of you know. And but the point is that effective theories, by definitions, they are powerful, they are elegant because they need very few ingredients, but of course they do have limits. And it's very important to know which are these limits and where are these limits. And I think one picture that, let's say, describes very well effective field theories is a kebab. So a kebab, of course, is, you know, is a big chunk of meat, which with certain properties, like it looks like meat, it tastes like meat. But of course, most of the time, you don't know where these meats come from, right? And once you order your kebab, these microscopic details is completely lost, is hidden somewhere, okay? And this is one first feature of effective theories. So the details are somehow hidden, and the details are what is pertaining to the microscopic. So the microscopic are hidden in the parameter of the EFT. And unless you have a theory behind that, a UV completion, you will never be able to, let's say, dig into that. And the second point, which is very important, is basically they have all the effective field theory, they have a kind of UV cutoff and a strong coupling scale at which basically they fail. And I think it's fair to say that almost 99, it's not 100% of the physics theory that we are working on are effective theory. So they always break down at a certain scale. And of course, I don't have to convince you that it's very important to know where that scale is. But despite all these issues, these effective theories can tell us a lot. And I will try to show you an example. Now, one other thing which is, I think it's very important and sometimes is it's a bit like, let's say, forgot, is that symmetries are useful also if they're broken. So in particular, symmetries are especially useful if they are spontaneously broken. And the reason is because in the technical jargon, we say the symmetries are nonlinearly realized and they give rise to extra degrees of freedom, which constrain a lot, not only the low energy dynamics, but only the interaction terms of these objects. So, and this is indeed something that we will use. This example here is a simple example, right, that summarizes what is a spontaneous symmetry breaking. You have just a system which is invariant under rotations, and then you let it evolve, it goes to a ground state, and clearly the ground state breaks the symmetry. And in the formal mathematical language, we say that some operator took a VEV, and this VEV that basically defined the ground states break the symmetry. So now, okay, this was a bit the introduction. Now I want to give you some example of that. And I want to start with something that I stepped upon like a few years ago, and which I find it's very tricky questions. And so the question is very simple. It's like we have a solid and we have a fluid, okay? They look quite different. They look like having very different properties. But if I ask you like more formally as a physicist, what is the difference? What would you answer, right? Can we make this difference or whatever it is more formal and precise at the level of, you know, equations, symmetries, and things like that? So for example, which symmetries a fluid have that a solid does not have? Okay, and I encourage all of you here to think about an answer, and you will see in a while we will get there. But I think it's a funny process to think about it, because it looks like a very stupid question, but it's not at all. Now, in order to introduce a bit, I will start from very basic things. So what is a solid? Well, the first attempt, you will say it's something that has a shape and the volume, which are fixed. So no matter if you put inside a container, that will remain fixed. A solid is rigid, so it looks like elastic, while a fluid does not. And from a more technical point of view, a solid, let's say, display the presence of transverse sounds, right? Which is exactly what you hear if you knock on your table. And then, as we will see, the main theory for solid, which is called Debye theory, implies some other, let's say, features for solid, which is the density of state goes like the frequency square, and we will see what is this. And the specific heat goes like the cube, right? And this Debye theory works very well. So it describes solids very well. Now, on the contrary, what is a liquid? Well, a liquid, again, paraphrasing what we said before, we can say, well, the volume of a liquid is fixed because it's not a gas that can expand, but the shape is not, right? So if we put inside a container, it will take the shape of the container. And in this sense, a liquid is not rigid. It's rather viscous. So this means that the liquids respond only to a shear strain rate, which is basically a deformation, which is time dependent, if you like. And okay, well, the physics of fluids is usually, you know, very well described by diffusion. And there are various steps to describe diffusion. You can start from Brownian motion, which is just, you know, a random walk, if you like. You can start describing it with some Langevin equation, so putting inside some kind of noise in the system and averaging on it and blah, blah, blah. Or you can start with the standard, let's say, hydrodynamic things and let's say some continuity equation. You will get always the same answer. That basically the dynamics of a fluid is described by diffusion. Now, I want to go back a second to the main statement that I said, which is probably the reply that most of you have given in terms of the difference between a solid and a fluid. So liquids do not have propagating transverse form. So this is the standard things. And this is related to the fact that liquids are not elastic. Now, I want to go 3 steps on this statement. So the first step is, can we derive this thing? I mean, and which is the symmetry behind this feature? The second thing, which is more like, you know, like an experimental point of view, is which experiment or how can I actually see that this is happening? And the third statement is that I want to really check if this that I'm telling you is correct. And you will see the answer is not. Now, going from the field theory point of view, well, the idea it's very simple, and it's the following. So our UV word, at least as much as we know, it's relativistic Lorentz invariant. So it displays basically invariance under the Poincaré group. And this is one of the fundamental symmetry, let's say, of our constructions. But it's clear that the low energy world where we live on does not respect this symmetry, right? And every phase of matter destroy or break spontaneously this symmetry, at least part of it, just because it selects a reference frame. So a solid selects a reference frame because there is a crystal, so there is a crystal structure. A fluid selects a reference frame because it's moving at a certain velocity, etc., etc. So the main idea is that relativistic Lorentz invariance is broken in the IR spontaneously. And the main idea is to classify the phases of matter, seeing how this Lorentz invariance is broken. So the different pattern will correspond to different kind of phases. And this idea goes back to a very nice paper by Nicoli, Spenco, Piazza, Rattazzi of 5 years ago. And let me give you just a few slides of context. So the first step to be modern is to build a field theory language. And the field theory language works this way. So we will use a set of comoving coordinates, so some scalar fields, which parameterize just basically the position of a particle. So you can just imagine of following, let's say, a molecule or whatever it is, and sitting there. This will be your scalar field. Now at equilibrium, this scalar field will be just coincident with the coordinate, okay? So it's just a label that you put to a coordinate there. And then what you do is that clearly you can go deforming this scalar field, and this will be the deformation, the excitation that you are doing. So you are kind of deforming this system, and this will correspond, if you like, to the low energy excitation, the phonons, if you like. And there is one assumption which is very strong, but it's actually quite, let's say, intuitive, is that, you know, every one of these phases of matter at large distances look homogeneous. And for simplicity, I will also take it to look isotropic, even though it's not necessary. So in the homogeneity assumption, you can understand it very well looking at your table. And it's clear that your table is not homogeneous. Yeah.
Sorry, you write a vector field there, not a scalar field.
Well, it's a set of scalar field. So basically, it's just a collection of scalar field. Depending on the dimension that you have basically a set of things. But you can think as basically a vector composed of all these scalar field, if you like. Yeah. But this I here would be basically one for every space-time direction, if you like.
May I ask a question too, Matteo?
Yeah.
So you also put the superfluids there in the previous slide.
Yeah.
So scalar superfluids, you don't think you are breaking any other symmetry that is not inside Lorentz?
So the superfluid, usually the way we see a superfluid is is like, you know, the spontaneous breaking of a U1. And in this language, there is something which can, there is a simple way to actually build a superfluid, which is taking this scalar to be in the time direction. So if you take it in the time direction, basically this guy in the time direction with the coefficient proportional to the chemical potential is exactly the effective field theory for a relativistic superfluid. So the point is that you are used to see the superfluid in a different gauge, because you of course, these objects, as you will see, are not gauge invariant, and you can always take you know, a gauge where these guys are set to 0. And that's what you are used to. But in principle, you don't have to. And you can describe a superfluid exactly in these things. So I will not talk about superfluids today, but there are nice papers by Son and friends where they describe superfluid exactly with this language. I can send you the reference after.
Okay.
Yeah, so let's go on. So there is a kind of field theory language to do this. And so under these assumptions, it's clear that at lowest order, since I want this homogeneity and this shift symmetry, the only thing that I can write down is basically derivative objects in terms of the scalar. And here it looks like very complicated, but at the end of the day, it's just a matter of deciding which scalar object you can construct in terms of this matrix. And one is clearly the determinant, and then you have the traces, okay? So depending on how many dimensions you are, of course, you have more traces. But if, for example, in 2 dimensions, you only have 1 trace because the other are not independent. And then that's it, basically. Then you can write your action, and the action looks very simple. It just looks like, you know, a generic function, which we will discuss, function of the determinant of this object and the trace of this object. So this, I claim, is the generic, let's say, action at 0 temperature for a solid, a fluid, and any phases of matter that break spontaneously the Poincaré group. And now what is the pattern? Well, the pattern is that, of course, space-time translations are broken spontaneously because the scalar take basically an expectation value which is linear in the coordinates. So this is not anymore a symmetry. This is also not anymore a symmetry because you can convince yourself that if you set phi to be xi, clearly this is not a symmetry anymore. And they break down in a very specific way, which is necessary to retain homogeneity. So they break down to the diagonal subgroup. And then this is very important because you can convince yourself that if you write down the stress tensor, the stress tensor is homogeneous. Okay, so you don't get any spatial dependence in the stress tensor. Now, okay, where all this mess that I'm telling you wants to go? Well, it wants to go that in this language, you can understand very quickly what is the difference between a solid and the fluid at the level of symmetries. So if you do the computation, which of course are quite boring and long, you will find out that the elasticity related to this action is proportional to the derivative of this function with respect to x. And then the speed of these phonons will be exactly proportional to this g. And now, well, you know, right? We go back to this statement, and I told you, well, in a fluid, there are no propagating shear waves. So you have to set this velocity to 0. So this means somehow that a fluid, it's basically a system where this function is depending only on the determinant. And here comes the beauty of the effective field theory, right? So is this kind of term or this kind of action protected by symmetry? And the answer is yes. So there is a symmetry which the determinant has and the trace does not, which is called volume preserving diffeomorphism. So imagine to take basically a change of what we'll call a change of coordinate or a field redefinition, but to take a field redefinition such that the determinant of the Jacobian is unitary. So this means that you are doing a transformation in your field, which you're certainly allowed to do, but the volume you are keeping it constant. Okay, and you can see that the determinant satisfies this, but the solid does not. And this symmetry is exactly the symmetry that distinguishes solids and fluid, and is exactly, if you want, a fancy way of saying that the fluid takes the shape of the container. So this is a nice example where basically we can formalize with symmetry something that we see with light. Yeah.
This assumes the fluid to be incompressible.
That's a good question. Yes, I think I'm assuming that. Yeah. But I think, let me think about it. No, actually no. So there is also bulk modulus here, which takes care of the compression. So here I only talk about shear part because basically solid and fluids, the longitudinal sector is very similar. So both a solid and the fluid compress somehow, but the response in the transverse sector is very different. But you can compute also with this action, basically the bulk modulus, which is what you are saying, what takes care of the compression, if you like. And it is finite. Actually, well, it's finite. It depends on this function. So in principle, depending on this function, you can have a compressible or incompressible fluid, setting basically the bulk modulus to be 0. But in general, this effective field theory takes care of both compressible and incompressible objects. Now, of course, there is another thing which I think is very important, which is the following. So solids, perfect solid and perfect fluids is pure fantasy. So they do not exist. All of the materials in real life are viscoelastic, and they keep a bit of solid features and a bit of fluid features. And they combine the two in a complex dynamics. And here you have some examples, you know, from, I took mozzarella cheese first just because, you know, I'm Italian. So that's the first thing I think about it, but there are plenty of. And here you can see basically what does it mean being viscoelastic. So being viscoelastic, it means the following. If you are in a perfect solid, you will put basically a strain, which is nothing else than you are deforming. So imagine you take, you know, your pen, my pen here, and you deform it, and you keep it constant. So if this material is elastic, perfectly elastic, it will respond exactly with no delay and exactly with the same form. So the stress that I will produce will follow exactly the same time shape of the strain. On the contrary, if this material is viscoelastic, it will relax. So it will have a delay, and this delay is given by the dissipative component, which is basically the viscosity. And this brings us to understand what is the experimental test that I will do to see if something is a solid or something is a fluid. And the experiment is very simple. So you take your material, whatever you have, imagine your toothpaste, for example, you put it in the middle of two plates and you strain it. So you apply like a rotating, like a periodic strain, let's say a cosine, like I wrote here. And what you measure is basically the response, the stress, the force that you produce. And here you see 3 types of different situations. So the first situation is, as I told you before, is a solid. So I put a strain and the response that I get is exactly in phase with the strain that I put. And it's just multiplied by a factor that tells me how rigid is a system. A fluid, on the contrary, the response will be completely out of phase. So if it's perfectly viscous, it will be pi half the phase. And of course, any material in the middle will have a certain phase and a certain amplitude. Now, how we make this mathematical? Well, we say that, you know, if we say that, for example, the stress is a simple cosine formulas, is cosine expression, then the strain, it will have a different, let's say, amplitude, but also phase. And in terms of, let's say, what these people do, they use what is called G, which is called the complex modulus, which in our language is nothing else than the 2-point function of the stress tensor. And of course, in general, this guy will have a real part and an imaginary part. And then, as you can imagine, the phase is just basically the ratio between the two. and the amplitude is the modulus, okay, if you decompose this complex number. And of course, everything will depend on the frequency of these deformations that you do. Now here we go. And this is what you get from experiment. So this is what I was telling you. The real part takes care of the elastic part, and the dissipative part is always the imaginary. And this is obvious also because if there is no imaginary part, there is no phase. So that's a solid. And these are two plots, which are what you find in all the fluids and the solid. So what you see here is that, let's start from the solid because it's simpler. So what you see is that the real part is actually much bigger than the imaginary part. Okay, so this means, and it's more or less constant. So this means that the response of these things is mostly solid because basically it's all driven by elasticity and the dissipative part is very small. On the contrary, in a fluid, what happens is that is exactly the opposite, and at low frequency, who wins is the dissipative part. And the dissipative part has a linear shape at small frequency, which is what we call shear viscosity or viscosity. So the linear shape of this G second here is exactly the viscosity. And now we go to something which is very puzzling, and I find it very, curious, which is the following. Then I'm an experimentalist, okay? I come to IFT, I knock at your door, and I show you these plots here. Oops. So I show you these plots here, and I ask you, okay, I have this material. What is this? It's a solid or it's a fluid? Well, let's look at it, right? So here I don't see any phase. And here I see that G prime is much larger than G second. So I would say that's a solid. And then the experimentalist will tell me, no, actually I did it on water. And that's what I got, right? And this is what appeared actually in 2012. And it was quite shocking for the full rheology community. It was the statement that liquids support propagating shear waves at low frequency. And liquid behave like elastic solid. So why people were not surprised if this was happening at high frequency? Well, because it's well known that a liquid at very high frequency behave like a solid, okay? You can just try yourself to jump from a high trampoline in the water. That's what you will feel. But at low frequency, you will think that a liquid is very different from a solid. And this experiment will tell you the opposite. And there is something here in these slides which you have to focus on, which is very important. And it is this number here. So you see this scale. So this scale, which is more or less, let's say 1/10 of millimeter, it's very important. And it's the full story here. So why? Well, because size matters, and that's what we see in these liquids. So here is the same experiment performed at different sizes. So what you do is basically you probe smaller and smaller sizes. And that's what you see. So if you have, sorry?
What do you mean by size? Size of the recipient, size of what?
Yeah, so this is, so basically in the experiment that I show you, the size is nothing else than basically the distance between the plates. So if you do more accurate let's say, experiments, like you are probing something with, let's say, some wave, then it's basically the wavelength of the wave you are sending to probe the system, okay? So you have to think as basically what is the characteristic scale at which you are probing the system, okay? And you do this experiment, and you can do it here.
Sorry,
yeah.
Can you describe again the experiment?
Yeah. So the experiment, well, the simplest one is basically this experiment here. So you take two plates, okay, and you put your liquid inside, and basically you start rotating one of the plate at a fixed frequency. And what you put is basically an apparatus which can measure basically the torque on these things. And on the other side, you measure this force. And with certain computation, you can deduce what is the stress that is induced. And you can basically compare the two. And when you compare the two, you basically get two curves that look like, let's say, like these two curves. And then you can extrapolate what is called G of omega, just by this definition, basically, right? So it's basically, if you want, is the linear response, is the 2-point function of this guy. So you go to Fourier space, right? You get basically, and then in Fourier space, this is just the normal product, and you can extract what is G of omega looking like. And they will have a real part and the imaginary part, and that's exactly what is plotted in this paper, in this plot here. So this is the real part, the red, and that's the blue is the imaginary part, and this is the frequency at which you are rotating the plates, okay? And this is the size between the two plates, Okay. Now here you have to be very careful because basically what you have to do is you have to avoid in any possible way that the boundaries have effects on this. Okay. So you don't want, of course, your boundary to mess up with your computations. And there are certain procedures which I'm not expert of to basically avoid these boundaries. And of course, this becomes harder and harder the smaller you go, of course. And this is what you see. So you see that basically at large distances, so let's say 0.7 millimeters, this looks like pretty much like a liquid. Then there is a kind of transition. And then you go to a regime where this looks totally solid. Okay, so this tells you that even at small frequency, changing basically what we will define as the momentum, the system behaves completely differently. And there is also something very interesting, which is there is a scaling of G prime in function of this distance. And it scales like L to the cube, to the distance to the cube. And there was a nice paper by some of my collaborators that appear in Proceeding of Natural Academy of Science, where they extrapolate these things from theory. So it's pretty cool. And for those of you who are curious about hydrodynamics, well, this tells you a lot also about the regime of validity of hydrodynamics. And I just posted a preprint some weeks ago about this. So if you're curious, just have a look. So now the question is, how do I understand this? Okay, so that's the task. And well, the point is we have to think a bit more about what is a liquid. And so a liquid is, you know, yes?
Sorry. But if I haven't misunderstood what you said in the beginning, when you have something which is solid and something that is liquid, they have two different symmetries that they have to obey. Or in other words, the order parameters should be, let's say, different, or the operators that you know, take place there are different. So what is this kind of phase transition, or what are the operators which we are going to change in this?
Very good question. Very good question. So as I told you before, I was talking about effective field theory and spontaneous symmetry breaking, and that description is valid only at very low momenta. Okay. So for example, if you have a Goldstone boson, imagine, for example, a phonon you can derive from spontaneous symmetry breaking, which is linear in momentum, like any, you know, well-being Goldstone. But this is true only at small momenta. So the Goldstone theorem, if you like, and these symmetries will not tell you anything of what's happening at higher momenta, just because they don't have that power. So there is actually right now, and I will go to that point, there is a lot of discussion to try to understand if you can think of this transition that I just told you in terms of symmetry. And there is a possibility, and I will just mention it at the end, but it's not, let's say, a standard phase transition. So at the moment, nobody knows if this is a clear phase transition on a Landau, where you have a clear, you know, like expectation value, order parameter, and whatever. And the question is, okay, exactly what you said. If there is, what is that? So what is the order parameter? Okay. And so this is an open question. It's a very good question, actually.
I see. Thank you.
Welcome. So yeah, if we go back, we have to think about liquids as basically, you know, a collection of molecules that differently from solid. So in a solid, these guys will just oscillate around the equilibrium position, right? And in a liquid, no. In a liquid, they also jump around. And so there is a kind of rearrangement of molecules. And this rearrangement goes with a certain average time, which we call tau. And of course, it involves some jumping, some potential. So it needs some energy. And so there is a theory that tries to explain exactly what we see, which is made of a very simple assumptions. And it goes back to Maxwell. And so the theory is the following. So imagine you have a shear wave equation. So just, you know, the standard wave equation. So it will be like the first term in this equation and the last term. But now instead of taking this equation, takes the simplest possible deformation, which is the following: add a dissipation time, a relaxation time, if you like. Now, if you consider this equation, and there are good motivations to consider this equation, and phenomenologically, this tau should correspond exactly to this time of jumping that I was telling you. Well, you solve this equation. Okay, it's a very simple equation. You get two modes. And the funny thing is that then if you check the real part of this mode, well, what you see is that at low momenta, below a certain cutoff, the real part is 0. And the dynamics is at low energy dominated by a diffusive mode. So this is exactly what you will expect in a liquid. But then when you go at high momenta, well, there is a collision between this diffusive mode and something else. And there is a mode that becomes propagating. And you see that at high enough momenta, basically it's a totally perfectly fine waves propagating. So basically here you see that there is a transition, which is driven by basically going to smaller scale between a liquid behavior and a solid behavior. And this is basically one of the theory proposed. And we had a a long review in physics report where we try to extrapolate all the features of this thing. And to be fair, I don't think it's fair to say that this goes back to Maxwell, because actually the first guy to write this equation was Heaviside, the one of the step function, and he wrote it for something, you know, very, very pragmatic. So Heaviside was an electrical engineer, okay, he was not a physicist, and he was working at the time with, you know, the equivalent of our Zoom call, so with the telegraph. And apparently the telegraph is, you know, well described by this circuit. So don't ask me too much about why, but this is the circuit. And well, you can do, you know, the things that you learn at the first year of graduate studies. You can solve this circuit and write down your equation using your, you know, Kirchhoff laws, etc., etc. And you find out that basically the equation that you get looks like this. And if you forget this term, basically the equation looks exactly like this equation that I wrote you here. And the funny thing is that you will find also a cutoff momentum. And this cutoff momentum for the telegraph is around the inverse of a kilometer. So this is quite funny because in liquids, if you compute these things and there are simulations and experiments, well, this guy is Armstrong. So you can see basically it's the same equation, but talking about completely different scales. Now, what is the physical meaning of this scale? Well, this scales is basically telling you that there is basically a region in which, inside which the wave can propagate. So the wave cannot propagate at all distances, but they are somehow confined in small bubbles in a liquid, whose distance is exactly given by the c, where c here is not the speed of light, of course, it's the speed of sound, and tau, which is this time. So basically, if you go, you keep a liquid, you take a liquid and you go a distances so short that you can probe basically the dynamics that is happening in this bubble, what you will see is not the physics of a fluid. It's a physics of a solid, okay? And the theory to understand that, at least the only theory that I know, is the theory that I just showed you. And this is quite interesting. And so what we tried to do was basically to try to, you know, this equation that I show you, if you read the original paper by Maxwell and then there is a follow-up by Frenkel, famous Russian physicist, it's quite phenomenological. Actually, they put it almost by hand, by some intuition that, you know, they had. They're great physicists, so I don't know where they got it from. But there's no, let's say, formal derivation of this thing. And what we tried to do was a very stupid thing, which is...
Sorry, Matteo, a question. Sorry to interrupt. So in the case of the telegraph, what does this scale mean? Just physically, I mean, above,
very good question.
above a kilometer, you get too much noise? Or...
Yes. No, it means it's the wavelength of the transmission that you can actually transmit. So if you have your telegraph and you try to transmit something at wavelength which are larger than this, you cannot. That's basically what it's telling you.
Yeah, but we know with telegraphs you could send messages like across Europe or whatever. So how did they overcome that? Yeah,
I believe that, but I don't know, that is the second term playing a role. But it's a good question. So I don't know, actually, I discovered it just randomly that, you know, this equation here is called the telegraph equation. Okay. And of course there is a reason. And if you search in the telegraph equation, you search that basically you find out that Heaviside has a very old paper that if you're lucky enough, you can find somewhere. And he described these things, but that's a good question. So that's a good question what it means here. It must have to do with basically the propagation of the signal inside this wire, something like that. But now I have to think, yeah. I have to think if it's related to the size of the wire or the wavelength of the communication. That I don't know. That's a good question. We can think all about it. So tonight you know what to search in Google. Okay, so let me go back to this. So yeah, then what you want to do is basically, okay, I want to... Sorry? Nothing? Okay. So yeah, then Is there a question or?
Yeah. No, I think somebody's voluntarily unmuted, but. Okay,
no problem. Then, so then the next step that we wanted to do is like, well, you know, we are theorists, and then we said, okay, I want a field theory of this. And the problem is that this field theory is very hard. And let me tell you why. So you start from something, and that's the following. So you want to add, of course, the field theory for a wave equation is super simple, right? You can just write down Klein-Gordon equation, you have a wave, dot. Now, how you add this I omega tau term? You have to think that this I omega tau term is due to dissipation. And then the idea that comes is basically, it must be related somehow to some viscous force. And if you think about the viscous force, well, the viscous force is of this kind. So it's like viscosity times ds over dt, where s is like the deformation. And then what you want to try to write is something like, imagine phi d phi dt. But then you encounter immediately a problem. So the first problem is that if you have only one scalar, phi d phi dt is a total derivative. So you can just throw it away. And then, of course, well, what is the next step? Let's take two scalars, and that's what we tried. So you take two scalars, now you can build these antisymmetric terms, and you can build basically your field theory, just, you know, standard terms plus this thing. So one thing which is very important is that these terms looks very nasty. And the reason why it looks very nasty is because it's non-Hermitian. But the important thing is that it's PT symmetric. Now, I don't want to bore all of you with the theory of non-Hermitian system. It's a huge chapter that is open these days. There are a lot of discussions about how to write down non-Hermitian field theory, what is the meaning, etc. But the only important things that you need to know is that even if this guy looks very nasty, it's a well-defined field theory. So the evolution is unitary, everything is fine, and you don't have any issue. Now, beside all the, you know, the technicality, what do we get? Well, we get that if now we compute basically the two-point function of the scalar, well, we find exactly the same thing, that there is a momentum, which is a critical momentum. Here is basically the orange line. And what you can see is the following. So if you go at momenta, which are higher than this, you see that the two-point function has oscillations. And this is the clear signature of basically a wave, right? So it's a solid behavior. On the contrary, if you go at momenta which are smaller than this, you see just something relaxing. And this is exactly like a fluid, okay? So this is the time behavior of the two-point function. So this is a very, you know, simple field theory model that is able to do this. And okay, I lied a bit. I told you that I won't talk about holography, but I want just to tell you that actually I came, you know, to this topic because of holography. And in holography, something like this is happening, and it looks like, you know, basically the things that you get from holography, which are left side of this screen, are quite in agreement with the things that you get on the right side. Now, because I'm very bad with time, I will skip the details of this, but if some of you are interested, I can go back at the end of the talk. Now, going back to the question I got, which is a very, very good question, you know, once we want to change the symmetry, chase the symmetry. So what is the symmetry? What is going on at this transition? Is something happening? And can I understand this kind of equation from a symmetry point of view? Well, I think that the paper that went closer to get this answer is this paper that I posted here, and the theory is called quasi-hydrodynamics. Don't ask me why, I think it's a very bad name. But anyway, what they find out is that imagine you have a system with a bunch of quantity which are conserved, okay? So for me, the quantities are these big balls, and they are conserved. So if they are conserved, you can see that they propagate forever, okay? Just by definition. And then what you find is that imagine one of this quantity, one charge, whatever it is not conserved, but is slowly relaxing. This means that the envelope of this wave will decay exponentially. Now, if you assume that these charges are coupled together, what you end up immediately is this equation. And here is a simple, let's say, derivation in terms of two quantities. So I believe that if there is a symmetry, it must be related to something like that. And I will say something more at the end. Actually, here. So, well, what are the big questions? Well, one of the big questions as a theorist is exactly, you know, what we are stressing. What is the symmetry of this crossover? Is this a phase transition? Is there really a breaking of something? And how can you formalize this in terms of phase transition? And this is a big open question. I think one possibility is related to this higher form global symmetry that some of you might have heard. There are some, you know, this kind of new symmetry introduced by Seiberg and Gaiotto, and then, you know, replicated in various ways. And they must have something to deal with this. And then the other thing is that what is really the difference between liquid and solid, and is it really quantitative or qualitatively? I think there's this, all I told you goes to the direction that there is only a quantitative difference. It's only the size of this tau, basically. And of course, it would be nice to be much more precise on this. Now, I want to move to a second topic, which is the following. So I guess almost everybody of you has a glass close to you. And the question is, okay, what is this? What is this? Is a solid? Is a liquid? How does it behave? And is the same of a rock? And so the question is, we have to go back to our friend Debye. And Debye told us a long time ago that a rock has two important properties. So the first property is that the density of states, so the number of active degrees of freedom, goes like the frequency square. And this you at low frequency. And this is what you see here. Okay, this is exactly what you see. And this is somehow equivalent to say that the specific heat at low temperature goes like T to the D. And here you can see some solid, and all of them, they go very nicely with T cube, okay, before going to the famous Dulong-Petit law. So this is a solid, okay? And now we go to the glass. So if you take your glass, the simple glass possible is silica, and you do the same experiment, where you find out two quite stunning things. So the first stunning thing is that if you compute again this density of state, and be careful, you normalize by omega square, you find the peak. So this tells you that in a solid, this should be a line, but it's not a line. In a glass, it's a peak. And what is this peak? So this tells you that in a glass, there is an excess of state, and this peak is famous as being is famous as the boson peak, and there is a huge literature about it, and I think are one of the most aggressive people that I've seen in my life in conferences. I almost see them punching themselves to basically, let's say, dispute what is the origin of this guy. And there is another very funny feature, which is the specific heat of a glass does not follow Debye's law. So at low temperature, it's not Tq, but it's actually T. And there is a very famous theory also here, which is called two-level state by Phil Anderson, very famous condensed matter guy, which claim that, you know, these come from this two-level state, but still there is a lot of debate. And all the theories related to glasses, in a way or in another, come to the conclusion using the fact that the glass is a disordered system. But in the last, let's say, 6 to 8 years, there have been a lot of experimental, you know, progress, and the same properties of glasses have been observed in ordered crystals and in incommensurate structure. Actually, one of the guy working with ordered crystal, it's here in Madrid. It's here at the university in the physics department. It's Miguel Ángel Ramos. They do cryogenic thermal capacity measurement, and they see exactly that in ordered crystals. So what this means, well, for a theorist, this means that all these theories are bullshit, or at least they are not universal, right? It cannot be the final explanation because in these systems, ordered crystals or incommensurate structure, there's absolutely no disorder. And that's, so then we have to go back to our EFT and we have to think about it. So all this Debye theory come from one statement. And the one statement, fundamental statement, is that the main excitation in a solid is a phonon, and the phonon of this kind. Now, the key point is that in glasses, it's not clear at all if this is the end of the story, if the phonon looks like this, or maybe, since we are in Halloween time, maybe the phonon is a bit weird. It's a bit dressed up in a different way. And so that's what I work out with a collaborator in the last 1-2 years. So we had a lot of papers going on this. And I don't want you to look too much at the details. So the important thing is that we have very simple theories based on EFTs and on the nature of low energy collective degrees of freedom that might be able to explain this kind of feature without, let's say, using disorder. So as far as we know, for example, the first theory that we have, which is published in PRL, is basically the only theory that I know which is able to explain this excess here in order phases. And there is a lot of work going on in this field, which of course, probably, you know, you don't see it because it's not published in the PTH, but it's a very important thing. And, you know, most of the people say that the glass problem is one of the biggest one. Indeed, there is, you know, a big collaboration by Simons, the same one that, you know, funds high energy research, which is called the glass problem, cracking the glass problem. And it's €1 million collaborations. So now, yeah, in the last 5 to 10 minutes, I will try to argue on a different thing, which is even more interesting, which is the following. So I think most of you have seen this kind of picture, especially if you go, you know, in the south of Spain, and if you go in a building architecture of Arab origin, you will find a lot of these tilings, which are very cute. And so the question that I want to ask to you is if in your opinion, well, this kind of things is the same of this, okay? And so these funny tilings are called aperiodic crystals, or in another word, quasicrystals. And you can think about it like something in the middle between an ordered crystals and a complete amorphous system. So an ordered crystal is something, of course, which has a very nice periodic structure, like this square here. And an amorphous system, like a glass, is something completely disordered. But there's something in the middle. Well, the something in the middle is that you have something which is ordered. Okay, so there is an order, a long range order in the system, but it's not periodic. And so one example, it's what is called like Penrose tiling. So Roger Penrose thought a lot about these guys, and you can find in the web a lot of figures trying to, build and classify these systems. And one other, let's say, more real situations is what is called incommensurate charge density waves, which have a lot of, a big role in this discussion about ITC superconductivity and blah, blah, blah. And well, what I want to tell you is that also that these kind of things exist. And there is also a very nice story where one of, the most famous cosmologists was involved, Steinhardt. So he was involved and he studied a lot these things. And of course, they got a Nobel Prize, the people that discovered this kind of object. They got it in chemistry, not in physics, but these are very cool things. And how you can see them? Well, you can just do Bragg diffraction, which is something very common in crystallography. And you really see that they have this kind of structure, and you can really see that this is not periodic, right? And now skipping the details, well, the funny thing in these systems is that there are not only phonons, but there is an additional mode, which is diffusive, and which is called phasing, okay? And that's basically what it is. Okay, you can see here, this is basically 2 experimental papers where they see this mode. So it's like a solid, but in addition to the solid, you have a new degrees of freedom, which is there because of this non-periodicity. Now, how can we understand non-periodic thing? Okay, this picture looks very complicated, but is actually very nice. So there is a mathematical theory, which I find very fascinating, which is the following. So the statement is the following. So take an aperiodic system in D dimension. You can always see an aperiodic system in D dimension as a periodic system in 1 dimension more, cutted at an irrational angle. Okay, and this is exactly what this figure is showing you. So here you have, if you concentrate on the blue dots, this is a very nice periodic 2-dimensional square lattice, easiest thing you can imagine. And now let's imagine to cut it with a line. So if you cut it with a line and the angle of this line is actually rational, let's say, I don't know, 45 degrees, you can convince yourself very easily that if you project this guy on the line, you will get a structure which is periodic. The periodicity will be different because, of course, you have an angle, but it will be periodic. Now, if you do the same thing with an angle which is not rational, let's say square root 3, then you will find out that the structure that you see is not periodic anymore, but it will have some imperfection somewhere. So, for example, if you watch again these slides, you can see pretty well that at a certain point, if you call the long distance L and the small distance S, there is this pattern. And at a certain point, instead of having 2 long, you have 3 long. So this guy is not periodic, okay? Now, why I'm telling you all of this? Because, well, from this picture, which is very mathematical, you can understand where these modes come from. Because, of course, if you're doing a projection on this basically line, the projection is invariant if you shift this guy up and down, right? But the position of the balls in this, basically in this structure, jumps. And more precisely, once you shift this guy up and down, you produce some jumps between LS to SL. So you can see, for example, here you have LS, and then you jump to SL. And in real space, what are these jumps? Where you are basically rearranging the position of the atoms, okay? And these, again, are kind of jumps. So there are these phason jumps. This is basically the physical reasons of this guy. And then, well, you're curious, you start reading things, and, well, you read in this review that there are mode counting arguments and Goldstone theorem that tells you why this guy is diffusive and blah, blah, blah. And you can find a lot of basically blah, 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 not telling you anything. And then, well, with a friend and a colleague, we started to think about this problem, and we wanted to find a reason why this guy is diffusive. So what is the symmetry behind this guy, right? And that's what we did. And in order to do that, there is an additional, let's say, complication, which you have to take care of systems which are at finite temperature. So you cannot do the standard field theory that we're used of, but you have actually to do what is called Kalish-Schwinger. So depending if you are Philo-Russians or Philo-American, you call it Kalish-Schwinger or Schwinger-Kaldish. But basically the main idea is related to the fact that you have to double your degrees of freedom, do a kind of contour, where one of them goes forward in time, one goes back in time. And then the main let's say, way to see this is that there is a combination, which is the plus, which corresponds to your classical field. So this will be really the VEV, the quantum fields. And there is the difference of these two fields, which is basically determining the fluctuations, the dissipation part. And notice one thing, that this looks like very, very similar to the field theory that we were doing before. And it's not a coincidence that in order to put dissipation in that field theory, you need two fields. And actually, one can do a map one-to-one to this formal Schwinger-Keldysh thing, contour, and that field theory that I was telling you, which is a simple toy model. Now, this is a lot of blah, blah, blah. And of course, I don't want to get into the details, but what I want to tell you is that basically, if you do this EFT for quasicrystals in a proper way, what you end up getting is exactly basically that equations that we already discussed plenty of times, and that we know at low momenta, it's basically a diffusive equation. And this is a very funny thing, because actually in the experiments, there are two types of experiments that, as I was telling to Daniel before, they can probe different lengths. And if you probe a quasicrystal at large distances, you will see that this phason is diffusive. If you probe it at small distances, you will see that it's propagating. And that's exactly why. Okay, and notice that you see this guy diffusive only because of this gamma term, which is totally non-Hermitian. And it comes from the fact, in this field theory, from the fact that you are doing some dissipative field theory. And there is a funny thing also, which I want just to mention very, very, very briefly. And this guy is a Goldstone mode, okay? And is a diffusive Goldstone mode. And I find it very funny to try to understand what is a diffusive Goldstone mode. And I actually find out that this is something very discussed recently. And it's of course beyond what we're used, because we always say, right, we know about weird Goldstone boson, right, in the terms that they don't go like linearly momentum, but most of you probably never heard about diffusive Goldstone boson. Well, this is actually something that exists, and it exists in the dissipative system. And one of the systems where you can really see this at work are the flock of birds in springs. So you can see these flocks moving, and believe it or not, there is a Goldstone diffusive mode acting over there. So there is a very nice paper in Nature where they show how to get this diffusive Goldstone boson from flocks, which I find it very cool. Now, a few words about holography. Well, again, I wanted just to say that, you know, that's how I get here, right? So in holography, you find this mode. And so you do some kind of black hole fancy computation and you find this diffusive mode. And yes, it's exactly that kind of mode. And so, yeah, a few more words is that, you know, holography, at least intended as we use it, is an EFT. And it's actually much more than an EFT. And it's nice, of course, since holography is a kind of black box, to understand what we see in terms of some more standard effective field theory or hydrodynamics. And the three of them altogether makes a very strong, you know, team. And now let me just get to the conclusions. So the conclusion is that even if you just look around and you know you don't use a telescope, a collider, or anything like that, you will find a lot of interesting and cool physics around, and you will be surprised actually of the method they're using, and you will realize that actually are very similar and very close to the method you are using, and there are a lot of problems actually related. And yeah, the thing that I want to stress, and I'm speaking from experience, because I don't know, probably none of you know, but I did my master thesis in string theory. So I did a master thesis in M-branes. Don't ask me what they are, but you know, I was fascinated by the string theory at the beginning. But now now that I'm getting older, I'm getting more and more convinced that there are a lot of open questions without using any of these words. No super, no quantum, no hyper, no extra, no inno, no artificial. And I think they still need theories like us out there. And to give you an example, this is something that I'm working on these days. So it's in progress. We actually just sent the draft to Nature Communication recently. And the question is the following. So Debye theory is super well known, and it gives the specific heat of solid in a second. Well, believe me or not, there is almost no existing theory for the specific heat of liquids. So the specific heat of liquids, like you see here, goes completely the way around. So the specific heat goes down with temperature. Okay, and it goes down with temperature, and there's no theory that is able to explain this behavior. Okay, and furthermore, the density of state, which is what I was telling you before, goes linearly with frequency in a liquid and not quadratically. And well, this is, for example, something that fascinates me, and we are finishing this paper. So this is another work that we will post it soon. So this is another way to convince you that, you know, there are a lot of questions around that you will never suspect, but they're there. And as a theorist, you know, coming from high energy, as being, you know, part of IFT, I think we all share one thing. And the thing that we share is that, you know, we have an organizing principle, no matter what you are looking at, if you're looking at the sky or you know, down to the earth, symmetries, right? Symmetries are everywhere. We learn every day more and more symmetries, from topological symmetry or weird symmetries. And that's exactly what we use here. And the other thing I want to convey is that, you know, holography is not just an abstract black box that you don't trust, and somebody woke up in the morning and said, I told you that some brains are dual to some black holes, but it's actually very well connected in this EFT, what I call EFT trinity, which is basically, a combination of field theory, holography, and hydrodynamics. And I find this very fascinating. Before concluding, I want to thank you not only for listening to me 1 hour, but for having me here these 2 years. So very soon I will move from the swampland to Shanghai. And so nothing. I have been very happy these 2 years, and that's it. Thank you so much.
Okay, thank you, Matteo. That was very nice. Thank you. I have just before I open for questions. Is this swampland supposed to be Madrid?
Yeah, it is. Both because of the COVID and both because of the main team of research of IFT, I would say. Okay. Yeah.
All right. So, are there questions for Matteo? Comments? Remember to unmute yourself.
Hey, Matteo, I might have a question.
Mm-hmm.
Can you hear me?
Yeah, go ahead.
So this relaxation time, for instance, in liquids. So shall I think of it as what, a UV, like a UV cutoff or a IR cutoff?
Of what?
I don't know, for instance, because you were telling this idea of the waves propagating like in a bubble.
Yeah, so there is a very famous law in liquids, which basically is called Arrhenius law. And so this relaxation process is actually exponential in the energy barrier. So if you think at the energy barrier, like, a liquid having a lot of minimum, and you call this energy barrier, let's say U, then this relaxation time is basically the exponential of minus U divided T. So it's it's called the birelaxation, and it's a slow exponential relaxation. And if you think about the formal theory, like let's say hydrodynamics, then yes, you can think about these having a lot to do with basically, where hydrodynamics break down and things like that. But it's a relaxation process which is widely happening in all the liquids. And physically, microscopically, yes, it's exactly this kind of rearrangement of molecules from one minima to the other minima.
This is Alvaro. May I ask a question?
Sure, of course.
The stuff of the universe is also some sort of fluid. Do you have anything to say about it?
Yeah, actually, the only thing that I have to say about it is I have questions. And where this idea that, these cosmological models saying that the universe is a fluid come from? Why it could not be a solid, for example? That's something that I don't know almost anything about cosmology, but I find that, is the first thing, you talk about, Friedman, Robertson, Walker, or whatever, you do whatever. You take your stress tensor and you say, oh, this is a fluid. You put pressure, energy density, and and that's it. For example, what about the viscous effect? What about if there is some elasticity there? Would that change something for, I don't know, inflation?
Sorry to interrupt. Okay, so yeah. I mean, there are many models where you actually include also viscosity and so on.
Mm-hmm.
But to zero order, you just assume that everything is just a fluid, as you said, with some pressure, but then you can also add other stuff if you want. Okay.
What is
people have taken that into account. It's not.
And what is the idea? Why should be a fluid and cannot be have some small elastic component, for example?
Well, I guess to zero order because everything. I mean, the densities are so low. You just model it like a gas. Okay, with some pressure, with some density, some loss, because the densities are like 10 to the minus 27, whatever. So you to zero order, you just model it like that. But then you can also add other effects. Yeah.
I see.
Can I say one thing?
Yeah, sure.
This is an interesting question. So I think there are two important elements when we talk about the matter in the universe. So the first one is, and this you will be sensitive to it. This is symmetries. Right, and the reason why we usually consider what we call a fluid, and usually a perfect fluid, is because it's the thing that is compatible with homogeneity and isotropy. And maybe I'm going to say something wrong, but the behavior of a solid, for example, with respect to a fluid in this case, wouldn't be very different because there are no shear waves. There are no waves at all if you start from something that is purely homogeneous and isotropic. Just by imposing these symmetries, you eliminate it. The second important thing is that when we say a fluid, in particular perfect fluid, the important thing is that is the 0,0 component of the stress tensor that is dominant. And this is just because we are interested in the gravitational part of this energy. We just say that mass is the most efficient form of energy to generate gravitation. And that's really, this is really because of that.
I see. Thank you.
May I ask a stupid question about what you said?
Of course.
On the way. So when you talked about, so in the first example of the difference between between fluids and solids that you discussed in length, and in particular this kind of simple experiment to distinguish between them and the reaction of fluids to a stress. So the first thing that came to my mind when you described that was there was a dichotomy that would be it could be expressed in terms of the Reynolds number, but maybe this is not really that. So could you explain whether the two behaviors that you described, so when we're going to very small lengths for the length scales for the system, so is that really something that has to do with the Reynolds number of the perturbation? And if not, what would be why isn't that true?
So yeah, it's different because of the following reasons. So the Reynolds numbers quantify the amount of nonlinearities in the system, basically. So how much nonlinearities are important. And what I talk about is all at the level of linear response. So I'm not considering any nonlinear, let's say, effect, nor in hydrodynamics, nor in solid. So when you talk about Reynolds numbers, it basically tells you, when a fluid enters this kind of turbulent regime, which is due basically to nonlinearities. So when the nonlinearities becomes important. So this effect that I'm discussing has nothing to do with these nonlinearities. So
okay, wait, because another way to interpret the Reynolds number is also in terms of the relative importance of convection and diffusion. And this, I think, is also true at the linear level. So if I remember the numbers that you gave, so we had two plates separated by a fraction of millimeters, something like this. So to me, this is close to the regime of microfluidics, where we know that the viscosity of fluids becomes dominant and that it's the flows are laminar and everything. But I thought that this also had something to do with the linear response, but maybe I'm wrong.
Well, as far as I know, yeah, I never thought much about this in these lines, but I was thinking about Reynolds like something more related to turbulence. I mean, I know that the Reynolds number goes like the inverse of the distance. So, the smaller you put the distance, basically the biggest becomes its Reynolds numbers, or vice versa, something like that. So basically it becomes more important when you go to smaller scale. But I'm not sure that the effects I'm describing has anything to do with the turbulent onset or anything like that. So I'm not sure. So on top of my head, I don't know, but I don't see a clear relationship between any turbulent dynamics and what I've been discussing. So yeah, I don't know.
It's a pity because turbulence is not understood.
Yeah, that's true. I mean, there's a big effort in understanding. For example, again, we can ask the same question: what about symmetries in turbulence? Is there any symmetry? Why, for example, this Kolmogorov scaling is coming from any symmetry? Or it's a very interesting topic, but I think it's we know that it's much more hard, exactly because you go into complete nonlinear equations, and then I don't know. So I actually saw a paper like some months ago, which was very interesting, where the guy claimed to find a kind of field theory for turbulence. But I don't know exactly the details. I think it's a very fascinating field, of course, turbulence, right? Because it's another case like the one I was discussing, that you just go at the beach, you look around you and you see the whirlpool, in the river or wherever, and it's there and you don't understand it, right? And that's for me, as a theorist, it's very annoying because, I don't need a collider. I just see it there. It's in front of me doing its whirlpool and I don't understand it. And I don't know. You know, so yeah, I agree. It's a very interesting question, turbulence, but I have nothing smart to say about it, at least today.
Any more questions for
Yeah.
Matteo? Yeah.
I have one question.
Hey, Guillermo.
Hi. So you were discussing about glasses.
Yeah.
And you discussed about the apparently some discussion that there is ongoing about density of states. I think you said.
Yeah.
And a certain peak that
Yeah.
appears. Can you say something more about that? Or?
Yeah. So accordingly, if you take a solid, an ordered solid, and you follow the Debye theory, you can convince yourself very easily, basically in a second, is just counting the number of degrees of freedom in a sphere of momentum k, that the number of degrees of freedom, so the density of state will scale like omega squared. Okay, so this is something that you can really derive in 3 lines. And this is a very well-respected thing, okay? And it has to do mainly on the fact that, you know, the phonons are linearly dispersing. So you have these degrees of freedom which are dominating the low energy response, and they're dispersing linearly. And when you compute this in a glass, so there are plenty of measurements. You can do basically 2 things, which are Raman. So you can do Raman scattering, you can do neutron scattering, or you can go to some heat capacity measurement. But in all these 3 things, you see a peak, a low frequency, which is much below the peak that you will see, for example, in a crystal. So in a crystal also, there are those peaks, which are called Van Hoff singularity, but are due to the fact that basically you are approaching the boundary of the Brillouin zone. They have nothing to do with low energy. Here you see a peak, which usually is terahertz, so it's very low energy, some MeV. And this tells you that basically you have an excess of state there. So there is something else in a glass, which is going around, and it's not the standard phonon. And there was a huge dispute that goes back probably 50 or 60 years to try to make a model and to try to understand what is that. And there are several models. I think the most famous one is called heterogeneous elasticity, which tells you that basically in a glass, since you are in the disorder phase, the elastic modulus is not homogeneous, but it's basically space dependent. And you can do a theory, and if you actually, basically the theory is kind of simple, is imagine you take a system and you put, you know, some kind of areas with a certain correlation length, and you say inside this correlation length, the elastic modulus is homogeneous, but when you go away, it can move, okay? And then you do a kind of, you know, description of this. You have to do some kind of averages and blah, blah, blah. And you find out, for example, that there is this peak comes. And naively, why this peak comes or is related to the fact that, you know, if you are in a disordered environment, a plane wave is not anymore an eigenfunction because your system is not just a standard wave equation. So what happened is that this somehow has to be changed. And that is what happened. So now this theory is super acclaimed and, you know, very famous. But the curious thing is that, you know, people were for years and years saying that this is called a glass anomaly. It's very peculiar of glasses and it's due to disorder and blah, blah, blah. We don't understand glasses, etc. But more recently, since the experimental techniques are getting better and better and we have new materials, so people found out that basically there are a lot of situations where you see these things, but it's not a glass in the sense of a disorder amorphous state. And that's what I worked together with Alessio in the last 2 years. And that's still an ongoing question. So there are a lot of groups that are trying to convince both experimentally and theoretically. And the main question is, okay, where these things come from universally? And it cannot come from disorder. So there must be something else. It can reduce to disorder in the case of glasses, but it cannot be the universal answer. And the other big question is this feature really a feature of glasses or it's something else? Can appear also for other reasons somewhere else. And nowadays the community is, you know, going more and more into this second thing. And so just today, one collaborator, he sent me a very nice sentence by Schopenhauer, which I think described very well the situation in this field and in a lot of fields. When you have something new, some like kind of discovery or revolution of a paradigm. So the first time you get, basically people will laugh at you. In the second times, they will make a very strong opposition. And in the third step, they will say that it's trivial. And I think we are at more or less at the second step in this. So now people start not to laugh at you when you show these results and they start making a lot of oppositions. I do expect that probably in some years they will say that it's obvious, but we are not there yet.
And Pepe, can I ask one more?
Sure, sure.
Okay, so, but this is more basic, less technical. So I know well the first part that you described, the one about the EFT for solids and fluids, as you know. But then it got more and more complicated towards the end. But you still said that some of the things that you've been working on are effective field theories, right?
Yeah.
But I suspect that in order to describe some of the dispersion relations that you have and some of the modes that appear, you need to make at some point some specific choice of the Lagrangian, because the ones that you started with are very general, right? They just assume these general symmetries like translations or these diff invariants, on the volume. So what's the guiding principle that you use at some point to say, okay, I'm going to use this operator and not this other one, which maybe is also allowed by your symmetries?
Well, this goes back, in my opinion, a bit to the point of which questions you can ask the EFT, right? Mm-hmm. Because, for example, you know very well that, if you take these EFTs, for example, I don't know, the shear modulus depends on this function, the exact value.
Yes.
But the fact, for example, if that phase is a fluid, is a solid, or the dispersion relation do not depend on the form of that function, right? So there are certain general statements that depend solely on the symmetries. And these are completely independent of whatever function I put in my EFT. Now, there are other quantities which, of course, are dependent on the function. And for example, one quantity that I didn't describe is that you can make this EFT completely at nonlinear level. And you can study, for example, nonlinear elasticity. And if you study nonlinear elasticity, what you find out is that there are various behavior depending which potential or which function, what I call V, you put there. So basically, putting different V will mimic for you a different type of material. So I think about the following. So imagine, a solid, of course, then there are plenty of solid. And what I show you is what are the universal feature, right? So all the solid are rigid, all the solid, they have phonons, but you can convince yourself very easily that, for example, a rubber does not behave like cement, okay? And these differences are more encoded in, more details of the system. So for example, a rubber is very different from cement if you go to large deformation, right? A cement break, a rubber is hyperelastic material. And this kind of difference, for example, that you can see in the nonlinear response depends on the kind of potential. Now, when you ask like more complicated, well, the idea is always the same. It's always symmetry. But when you have to go, for example, at finite temperature, you have to be a bit more, a bit smarter. And, the point is that, of course, you cannot write the field theory at zero temperature is very poor in the sense that it loses all the effects of dissipation, etc. And for certain things can be good, like solid. But for example, for liquids, it's pretty bad because, as I try to explain, basically dissipation and relaxation mechanisms are the key. So you lose a lot of them. And the way you do that is nevertheless quite standard. You have to take these Schwinger-Keldysh techniques, which are kind of known, and you have to basically rewrite your full field theory that you know, but on top of this contour. And there you will encode basically this kind of, new dissipation effects, but the rules are always the same. There are some symmetries that you have to respect. For example, if you do this Schwinger-Keldysh, there are more symmetries known like KMS symmetry. So there are constraints coming from, unitarity, the thermodynamic law, and all these things. But the rules are always the rules of the EFT. It's the same game, just the game is a bit like, it's like when you are young and you pass from the motorbike to the car. It's the same thing. It's just a bit more advanced, but it's the same principle.
Okay. More questions? All right. So passing from the motorbike to the car is a good way of finishing the discussion. So thank you, Matteo. Thank you all for showing up.
Welcome.
And see you next week. Thank you very much.
Bye-bye.
Bye-bye.
Mm-hmm.